As the James Webb Space Telescope continues its cosmic odyssey, the images of distant galaxies and potential supermassive black holes stand as testaments to humanity's insatiable curiosity. The telescope's transformative capabilities not only captivate our imagination but also provide invaluable data for scientists worldwide. These awe-inspiring images serve as a reminder that the universe is a vast dynamic tapestry waiting to be unveiled, and the James Webb Space Telescope is our window to the cosmic wonders beyond. In the beginning, there was a Big Bang if you will. This massive explosion created the universe and filled it with the seeds of all the matter and energy currently present. But with that kind of turbo kickstart growth, something that ends after the initial blast isn't something that ends after the initial blast. The universe continues to expand, even accelerating as it goes at a rate referred to as the Hubble constant. The Hubble constant is an incredibly important number to pin down in the field of cosmology, but it's not an easy one to divine. In fact, it's so difficult to divine that the Hubble tension, caused by our inability to land on a single number, has become arguably as famous as the Hubble constant itself. And recent results from the James Webb Space Telescope have just re-cemented this tension as a very real problem to overcome. If a researcher wants to estimate the Hubble constant, they have two main avenues. There are others, of course, but the two most common are Cepheid variables and the cosmic microwave background. The cosmic microwave background is the leftover radiation still permeating the universe from the Big Bang. Using the cosmic microwave background is often likened by researchers to using a baby picture to predict what someone will look like as an adult. To some extent, knowledge about the universe's infancy should allow researchers to make predictions about its current state. Researchers have long used it to make inferences about the very beginnings of our universe and have used it to predict what the Hubble constant should be. Fairly recent cosmic microwave background calculations set the Hubble constant at around 68 kilometers per second per megaparsec. But the thing about theory is that you need to test it. And when the Hubble telescope launched, it became possible to do just that. Free of the constraints of ground-based telescopes clouded by atmosphere, the Hubble telescope was able to take extremely accurate distance measurements of far-off objects. And that's where Cepheid variables come in. Cepheid variables are a type of pulsating star that falls into a category of objects called standard candles. Objects that have a measurable and consistent brightness allowing us to fairly straightforwardly measure how far away they are. Measuring distances isn't easy in space, but it's crucial to being able to measure expansion. As convenient as it would be to stop there, there's one more step to the Cepheid method. Once their brightnesses have been divined and we know how bright a Cepheid is that blinks at a certain rate, we use those brightnesses to calculate the brightnesses of nearby supernovae. Then, using a quality called redshift, we use those supernovae to calculate the brightnesses of other supernovae that are even farther away. Because they're much brighter, we can see supernovae at much greater distances than we can see Cepheids. And because you can see the expansion of the universe better the further away you look, we look to the far-off supernovae for the ultimate calculation. This chain of brightnesses is referred to as a distance ladder, and you can't move to one rung without first calculating all the ones that come before. Over time, the Hubble telescope clocked distances for several Cepheid variables, the first rung on that distance ladder, which in turn allowed researchers to make an experimental measurement of the Hubble constant. But instead of agreeing with the prediction, it came out totally different, 73 kilometers per second per megaparsec. When experiment and theory diverge, it can mean one of two things. Either your measurement is wrong or your theory is wrong. And that, in a nutshell, is the Hubble tension. Which is wrong, the theory or the experiment? That is where James Webb can help. By observing in the infrared spectrum, it will be able to look straight through pesky clouds of space dust that all too often interfere with local astronomers' measurements. The Hubble Space Telescope, the previous tool of choice for local astronomers, has far more modest infrared capabilities. Its infrared measurements come at the expense of lower image quality, but James Webb can do both, observe in infrared and maintain high-resolution imaging. Crisper, dust-free images that Webb promises, the telescope is such a technological improvement that scientists expect its unprecedented infrared measurements might at last bridge a growing rift between astronomers over how fast the universe is expanding. And in a remarkable observation, the telescope took images of the same stars as the Hubble telescope and calculated a very similar Hubble constant. Although the Planck number disagrees from Hubble and James Webb's number by less than 10%, the discrepancy in the measurements implies that there's something terribly wrong with our understanding of the universe. Unless an error turns up in one of the measurements, it will take strange new physics to explain the tension. As cosmologist Adam Ree of Johns Hopkins University papers in the literature over the last 10 years have invoked anything from weird dark matter to weird dark energy to another exotic particle to a magnetic field in the early universe to a new field. All kinds of things. Some of these explanations look semi-successful, some of them look like failures, some of them would cause other problems. Developing a theory that might resolve the tension is still very much in the skunkworks or extremely speculative stage of trying to understand what the tension could mean. Like the Hubble telescope, astronomers using James Webb calculate the Hubble constant by observing flashing stars known as the James Webb Space Telescope continues its cosmic odyssey, capturing images of distant galaxies and potential supermassive black holes, serving as testaments to humanity's insatiable curiosity. Its transformative capabilities captivate our imagination and provide invaluable data for scientists worldwide. These awe-inspiring images remind us of the universe's vast dynamic tapestry waiting to be unveiled, with the James Webb Space Telescope as our window to the cosmic wonders beyond. In the beginning, there was a bang, the Big Bang, that created the universe and filled it with the seeds of all the matter and energy present today. This turbo kickstart growth didn't end after the initial blast. The universe continues to expand, even accelerating, as evidenced by the Hubble constant. However, pinning down this constant proves challenging, leading to what's known as the Hubble tension, a discrepancy between experimental measurements and theoretical predictions. Researchers use various methods, including observing Cepheid variables and analyzing the cosmic microwave background radiation, to estimate the Hubble constant. The James Webb Space Telescope, with its infrared capabilities, promises to offer clearer insights by overcoming limitations faced by ground-based telescopes. Its high-resolution imaging and infrared measurements aim to bridge the gap between conflicting measurements of the Hubble constant, potentially revealing new physics and deepening our understanding of the universe's expansion. One avenue of research involves studying pulsating stars known as Cepheid variables, crucial for establishing a distance ladder to measure cosmic expansion accurately. The James Webb Telescope's superior resolution allows for more precise measurements, potentially resolving the Hubble tension. Recent observations aligning with Hubble telescope measurements suggest promising progress in overcoming uncertainties associated with previous observations. Additionally, astronomers leverage the James Webb Telescope to explore water's cosmic journey, from its origins in molecular clouds to its role in planet formation. By peering into protoplanetary disks, astronomers gain unprecedented insights into how water transforms rocky planets into water-rich worlds like Earth. Recent observations have revealed water vapor in protoplanetary disks, challenging previous assumptions and reshaping our understanding of planetary formation. Overall, the James Webb Space Telescope represents a new era in astronomical exploration, offering unparalleled capabilities to unravel the mysteries of the cosmos. Its observations hold the potential to resolve long-standing questions about the universe's expansion and shed light on the fundamental processes shaping planetary systems, ultimately expanding